This is part 5 in a series of videos in which I am repairing this Wren computer. This is the third Wren I've been looking at over the last few months, and I have been kind of mixing and matching these videos as to which machine I'm working on. For the last few videos this has been this machine, and as I say, it's the third machine I've been looking at, and it's had a very wide range of faults. It's had track faults, a lot of ICs have failed, connector faults. I had a problem with the video monitor, and throughout the process of fault finding I've been trying to keep these videos as structured as I can. They do jump about quite a lot because of the nature of fault finding on a piece of equipment like this, especially when, as in this case, we don't have a schematic. But what I have been doing is trying to reverse engineer it, both the hardware and the firmware. And I've been doing that as part of the fault finding process. However, along the way I've been making statements such as I've been tracking down faults with certain buffers, looking at certain signal levels, reverse engineering to figure out how they're addressed. But I haven't gone into any detail as to how I've been doing that. So I thought what I'd do in this video is delve a bit deeper into this and explain a few of the methods I use to determine how a machine like this is laid out, and how the firmware and the hardware interact, and how you can go about fault finding on a piece of equipment like this when you have minimal technical information. So to start with, I couldn't quite figure out how to go about this in a way that made sense. So what I decided to do was to effectively explain this in reverse, so starting with the firmware and giving a particular example. So if we look at the what is now the first page of the firmware, I've been adding some notes to it. Recently found some technical bulletins that have helped to confirm some of this. I'm still working my way through that, but so far the information I've found luckily has been correct, and what I've been looking to do is to identify key values within the firmware. And if you're familiar with writing firmware, then you know that you will generally store certain variables in certain named variables, and they, when the software or the firmware is compiled, will be saved in a particular memory location. And then when you come to reverse engineer it, you've got to do the reverse, of course, and figure out what the value is that's stored in these key locations in memory. I've also been trying to reverse engineer the hardware, figuring out how the ports are arranged. And as I go through this, what I can do is start to replace memory addresses with human readable text. So for example, if we look at the second one down, for example, I've identified this memory location as being for this purpose. What I can then do is a find and replace for the entire source code, or the decompiled listing as this is at the moment. And it starts to make the entire code more readable. So if I give an example of that. So if we take a look at this block of code, we can see it's now quite readable. What I've done here, of course, is a find and replace for this particular variable. And originally this would have said LDA, FF07, meaning load into the contents of memory location address FF07. But of course this now saying load A with the video control byte buffer makes far more sense. So what this is doing is loading a copy of the video control byte into A. It's then setting bit 5, and it's then saving the new value back to the buffer, and it's writing that value out to port out to port 1. So what's going on here is the when we look at this particular port, it's a write-only port, so the firmware can't read the value, but it needs to manipulate individual bits, so it has to keep a copy of it so that it can do that. So that copy is stored in address FF07. So when it wants to manipulate a particular bit, then all it has to do is read the value from the buffer, and it can then manipulate the value however it wants. it saves the new value back to the buffer, so it's got a copy of it, and then it writes the value out to the port, and that controls the video. So I thought what I'd do is to continue through with this example and find out exactly how I discovered this was the video control byte, and what it does and what each of the individual bits do, and how that relates to the hardware, and how to find on the hardware the particular device that is controlled for this particular function. So it looks like a complete maze. It seems to be an impossible task when you first start looking at this, but once you've done this a few times it actually becomes fairly easy. The first thing to do, of course, is to figure out what the ports are. Now, I've covered this briefly in previous videos, but as I say, I didn't go into how I'd figured out what each port was and also what each of the devices on the board does. If we go back to the source code listing, and I've got here a list of all the ports I've identified so far. I've now been looking at what the individual bits do within some of these ports, because some are kind of bit values where each bit within the value performs a certain function within the hardware. But in order to explain how I go about determining this, I thought what I'd do is give a very simple example as to how in-out mapping can be put together for a Z80 system. So I'll just get the Fluke out of the way, and I'll give a very simple example as to how to design a Z80 in-out map, and then I'll do that in reverse and show how I use the Fluke to figure out what each of the devices were on this particular board. Okay, I've got my DaveCAD Junior CAD system here, and so what we'll do is design a very simple example of a Z80 in-out port mapping scheme. So if we look at the in-out map for the Wren, we can see that it makes use of quite a number of in-out ports, and the question is, of course, how does it go about accessing these particular ports. Notice that some are write only, some are read write, and really it's up to the designer to decide exactly how to create the in-out port mapping scheme for the system they're developing. Processors like the Z80 are extremely good when it comes to mapping in-out ports, and in fact it's one of the major strengths for the Z80 and the 8080 as well, that the port mapping scheme was extremely good. And one of the main things to do when you start developing a Z80 system is to figure out how you're going to access and address various devices within your system. So if we take the Z80 processor, then it's an 8-bit machine and it has a 16-bit address bus. So we have an 8-bit data bus, that's our data, and the data bus is of course bidirectional, so it can read data from the data bus and it can write data onto the data bus. It also has a 16-bit address bus, and that is of course used to determine the address that is currently being accessed with the current instruction. So when it comes to the in-out port system, then if we take a simple instruction such as out, and we'll say 7, 22, doesn't really matter, then what this instruction means is that we are going to send a value of 22 to port 7. But what does that mean within the context of the Z80? Well, firstly, the in-out mechanism within the Z80 only embeds the bottom 8 bits of the address into the instruction. So what this instruction will result in is a value of 7 being put onto the lower 8 bits of the address bus, and a value of 22 will then be put onto the data bus. Now, the out instruction does actually also load the upper 8 bits of the address bus, but it loads those from an internal register. Now, depending on how many ports you need to access, it's far quicker just to use the simple out instruction and ignore the upper 8 bits, so you don't have to load the internal register that's used to load the upper 8 bits. And what you do then is you just decode the number of bits that you require. So for example, if you're only ever going to access 8 ports, you only need to decode 3 bits. There's no point in decoding everything. It just means you'll get duplicate port numbers. So the way you'd go about doing that is, in my example here, we'll say we'll limit ourselves to just 8 ports. And the easy way to decode this is just to take an 8-bit demultiplexer. You'd feed the bottom 3 address bits, so that's A0 through A2, into the inputs of your demultiplexer, and then the 8 outputs are used as your port selection. So depending on the value that you put into your out instruction, so for example if you say out 7, that means all 3 bits here will be 1, and you'd select the uppermost bit of your demultiplexer. If you were to, for example, say out 2, then it would be bit 2 that you'd trigger. So this is how you decode it, but of course you can't just leave it like this and do nothing else, because these outputs would be triggered every time this particular address sequence was encountered. So what you then do is determine what you want to control with your in-out ports. So if you want to have an output, for example, then we'd select a latch of some sort, so maybe a 74LS 373, 374, depending on how we want to arrange the system, and that is an 8-bit latch. So our data buffer, so our data bus would go into the data inputs of the latch, and then this would be our output from the system. So this might be used to control LEDs or the video monitor or whatever you want to talk to through the particular port. Let's say we want this to be port 7. Then what we would have to do is have it triggered when we decode port 7. But we can't just feed this directly into this port. As I said, this needs more decoding to make sure that we don't trigger this every time we encounter address 7. And because we want this to be a write, that's when we're writing out to the system, so this would be an out, we need to look at the write line as well. So we would also need to decode the write line. So if we simplify and use an imaginary gate, then we're triggering when this bit is triggered, i.e. when we're at address 7 or port 7. Also when the write is active, that's when we're writing the value, but also it needs to be triggered by the in-out mechanism. So we also need to look at the in-out request line. So that would be another line that we would look at. And this means now that these 3 lines are only triggered when we have an out instruction talking to port 7. So we can now connect this to our latch input of our latch, and so we only write the value that's on the data bus, in this case 22, when we are outputting data to port 7. There may be other controls that you need depending on if you need to update the latch at a particular part of the cycle, in which case you might want to also include M1 or something else in your decoding. This is oversimplified. This wouldn't work if you just hooked it up like this. You need to take into account the levels, whether they're high or low, active high or low. But this is, as I say, oversimplified. It's meant to indicate how you go about configuring the system. So this would be an out. If you wanted to then have an in instruction, so you want to read port 7, then you could do something fairly similar. Again, you could use the same sort of latch, except you'd have it either way around. So your data would be on this side, and you're feeding data in, so you've got 8 bits of data. This would then go through to your data bus, so this is the same data bus. But again, you need to determine when this is going to occur, and very similar sort of setup. we'd have a bit of glue logic. It would respond to port 7, so it would be connected to this same point. It would also be in-out, and in this case we would need to look at the read line because we're trying to read data in, and that way this would be triggered whenever we have an in7 instruction. So that's the very basics of how the in-out port mechanism works on the Z80. It's a bit more complex than that, but that's fundamentally how it works. So the point here is, how do we go about determining what values for the port trigger which particular device? What we're trying to do is figure out what port number each device is and where those devices are on the actual PCB and if they're working. So how do we go about testing that? So we'll get back, look at the board, and then I'll just explain how I go about this. There are many ways you could go about this, but I find some ways much easier than others. So let's move the camera back so we can see the system again. So looking at the Wren hardware board again, I've got the Fluke Z80 pod plugged in. So I've removed the Z80 processor. I'll move the camera across so you can see the Fluke display. There will be nothing on the Wren display for this testing. I've shown in previous videos how to run tests to test the video RAM and put characters on the screen using a test program from the Fluke, and I won't be doing that in this video. In this video we're just looking at how to determine which of these devices is there to control which particular port, and how the Z80 accesses those particular devices. So I'll move the camera across. Okay, hopefully you can see that clearly. So what we have when we first start is the source code. So I've been through the source code a number of times and shown how to use the logic analyzer to try to figure out what each part of the code, or each major part of the code does. We've then used the information we've got from the analyzer to figure out what each of the key blocks of code we're doing, and that gives us instructions such as the one I showed, where we're getting an out to a particular port, and because we've got some idea now as to what's going on with this, we can try to start writing a map for the port definitions to figure out what each particular port is trying to control. And the next thing is to figure out which particular device we're looking at. So for example, if we're getting an issue with the video controller, we need to try and figure out which parts of the circuit relate to the video system. If we're getting problems with the RS-232, we need to do the same for the RS-232 components. Same with the real-time clock, the floppy drive controller. All the different devices can be controlled separately from the Z80 socket, and that's one thing to bear in mind. As I mentioned previously, although this looks like one huge circuit, really what this is individual elements all brought together to allow operation of a system, all under the control of a single processor. And so the processor must have some sort of control over these individual components, and that's what we're going to use the Fluke to investigate. So the first thing to do when figuring this out is to have a general look around the board, and what we're looking for here are multiplexers, demultiplexers, buffers, and in particular latches. Latches are fairly widely used for this sort of application. The two that I come across most often are the 74LS373, which is a transparent 8-bit latch, and the 74LS374, which is an edge-triggered 8-bit latch. They work in very similar ways in that they take data, an 8-bit wide data value, and that's latched into internal register, and those values can be output to the output pins, or the output pins can be put into a high impedance state. The main difference between the two is that with the transparent latch, when it's enabled, the output value always shows the input value, and then it retains that value when the output control is deasserted, whereas the edge triggered latch, the output only changes state to match the input when there's a clock edge. Other than that, they perform very similar tasks, but these are the sorts of devices that we're looking for. There are other types, but looking around this board I see there's a lot of 373s and a few 374s, so they're the ones that we are most interested in trying to figure out what's going on. So to figure out how this works, we've looked at the firmware, so we know that a particular port is going to give us access to a particular part of the system. So I'll power up the Wren and we'll start investigating port 1. So port 1 I've identified provisionally as being for the video control system. So the reason I've figured this out is looking at the source code. When we're trying to write to the video controller chip, it seems to be doing it through out 01 port values, and then it's writing different values depending on what it's trying to do. So what I've been looking for is where is the hardware device that's written to when port 1 is accessed. So what we can do is identify all the latches. Almost certainly there's a latch somewhere at work, and all we have to do is look at the enable pins for the latches and see which one is triggered when we try to write to port 1. And the easy way to do that, of course, I'll power up the Wren, is we can simply write to that particular port while looking at the enable line of the various latches. So if we start with this one over here, it's a 373, so it's pin 1 that we're looking at, and if we monitor pin 1 while writing to port 1, if that line changes state, then we know that latch is the one that's responsible for the video control byte. So we'll get the probe. Okay, so I'll put the probe onto pin 11. So pin 11 is the latch enable, so this is the pin that will be strobed if the system tries to update the value in this latch. And it's active low, so you can see currently it's high. If I try writing a value out to port 1, doesn't matter what value I write, so I'll write A8, and as you can see on the scope we got an update, so I'll just repeat that. So if you keep an eye on the scope, you can see that each time we write a value to that particular port, then we get some activity on the latch enable. Now of course I cheated here, I knew this particular latch was the right one, but if nothing had have happened then I'd move on to the next latch, keep doing that until we find the right one. There's only 5 or 6, so it doesn't take very long, and we now know that this particular latch is responsible for video control and it's accessed through port 1. Now I've been identifying the various functions for the bits on this port, and bits 6 and 7 are used to control the 2 LEDs on the keyboard. So bit 6 is the power LED control and bit 7 is for the caps lock light. Okay, so at the moment we can see that the power LED is on and the caps LED is off. Hopefully you can see that on the camera. The reason I wrote A8 to the port is because I happen to know that's the value that's written when the system starts up, so that's why I wrote that, so nothing would change. But what we can do now is write a different value to exercise this particular latch and see if the LEDs and the relevant circuitry around them works. So if we write out to the port, and in this case we know bits 6 and 7 control these 2 LEDs, and at the moment we have a value of A8 in those ports, so we know that bit 6 is low and they're active low. So if we want to turn the other LED on, so this is bit 7, we need to change the value from A8 to 28, so just toggling the upper bit. So if we write a value of 28, this should turn the caps lock LED on, and indeed it has. Don't know if you can see that, but the caps lock LED is now on. If I write a value out of A8 again, it should turn that back off, which it does. If we want to turn the power LED off, we need to set the bit 6 to a high, or in other words, we need to change the value to E8. So if we write a value of E8 to that port, it should turn this LED off, which it has done. And if we write A8 back to the port, it should turn the LED back on, which it does. So you can see we have full access to all the bits on this particular latch. The other bits, when I followed them through, go to enable and disable the display on the Wren. They carry out certain things such as flash, that sort of thing. So they are responsible for the basic video control system. They're not passing data for the video out, but they are controlling the video system. So they also switch between bitmap mode and text mode, for example. So if any of those are not working, then of course what I can do is look to see if the relevant bit on the latch is changing. I document it, write down what each bit does, and so by the time you've done this for all the latches that are on the board, you have a very good in-out map for the system. And a few hours work and you end up with something that looks like this. So that's what I was doing, and as I said, I have since been able to confirm some of this with the original technical bulletins. And so some of this is quite interesting. There's a lot you can do. You can look at the RTC data. So for example, if we want to read the RTC chip, which is this one, I know that this RTC is on ports 1C and 1D. I showed how I did that using the logic analyzer. So what we have to do is write to port 1D the address we want to read. So in this case we'll read address 0, and then we want to read the data port, which is at 1C, and that's currently a value of 7F. If we want to read the same port again we have to go through both steps. It's a real-time clock, so this value should be constantly changing. It's currently 7F, so let's see if it does change. Select the address and then read, and as you can see it's changed. So this is the real-time clock inside this device running, and we can do the same thing with all the various devices. So if you want to know if the A to D is working, we can do exactly the same thing and interrogate and manually run the A to D converter. We can select and read and write values to and from the various parts of the memory system. We can control the UART. We can turn the relays on and off one by one, so we've got relay control, and this is against a bitmap field, so we can turn these on and off. And if we really want to, we can exercise the floppy drive by writing commands to it. So as long as you know what commands to read and write, you can control the floppy drive manually using the Fluke. In fact, one of the reasons I developed this memory system that you may have seen me showing in some videos was because I write scripts that will allow me to exercise the floppy drive controller. So I have a separate memory card for each type of machine I work on. So for the Wren, I'd write a fairly simple script once I've got this information to allow me to exercise the floppy drive and fully test it. So once you've got all this information for a machine, when you come to the next one, it becomes much more straightforward, which is why I wanted a decent memory system for the Fluke. So you can go through all the different parts of the system like this. You can write scripts and upload them into memory and run test programs directly on the Fluke. You can fully test the video system, all the different parts of it, the keyboard controller, and if any of them don't work the way they're supposed to, so if you're having a problem with the A to D controller, for example, you can try and run it manually, get the scope out, start probing around. You can put the Fluke into loop mode where it's continually doing the same thing, and it eliminates all the other activities that normally complicate trying to figure out what's going on in a system like this. Normally if you just try and run this, there's all manner of things going on at the same time, and it makes it very difficult trying to figure out exactly what signals should be present on any particular device. But doing it like this, you can run one device and toggle one bit at a time, and that way you can trace it through and find out exactly where the problem is. And it does make it so much more straightforward. So for example, back to this port, if we were having problems, we couldn't turn this LED on, for example, we can now trace this back to the individual pin on this latch, and then if that turns out not to be working, we can follow that back and find out if it's been addressed, if the latch enable pin is changing. If it's not, we need to go back further and look for the demultiplexer and the glue logic to find out why that particular pin is not being toggled. So, okay, I hope that made sense. If you want me to do more of this sort of thing and go into this in even more detail, then please leave a comment. It does get quite involved, but it is a very interesting subject if you're interested in this sort of electronics. Taking a board like this, you could spend weeks just playing with this and investigating it. And in the absence of a schematic, this is by far the easiest and quickest way to investigate a board like this. Sounds very long-winded, but it does mean that you can track down most faults very quickly. Some are more tricky if they're interactive, but in general what you can do is get the Fluke hooked up, and as long as you've got the board up to the point where it will run to a certain extent, that is, the Fluke's not crashing all the time, then this is an extremely good method for figuring out what's going on the board. But really, step one is to figure out exactly what it is that you're supposed to be looking at, and so that's why I started this series by trying to figure out the port mapping for the system. Okay, that's it for this video. Any questions or comments, then please let me know.